Now let's quickly try to solve the problem nth root of a given number. So the problem statement says here that we will be given a positive number n and a non-negative number m. And ultimately what we have to do is we have to find the nth square root of m and return the result. The nth square root of a number m is defined as the number y such that y is raised to the power n equals to m. Remember that here we will be given two numbers, one is n and the other one is m, and we need to find a number y such that if we perform y power n, we will be getting the result of m. So that is the simplest problem statement that we can get here. So ultimately we will have to find this value of y, we need to return that back to the user. So let's see a couple of examples so that you will have a better understanding. So here let's just assume y is what we are going to find and n we have gotten is 2, so y square is equal to 16. That means that y is nothing but 4 because 4 square is nothing but 16. Similarly here if we look at the second example, y is what we need to find and n is nothing but 3 is equal to 125. So here y is nothing but 5 because 5 power 3 is equal to 125. Similarly here another y power 4 is equal to 256. This is nothing but 4 power 4. So the value of the result that we need to return is nothing but 4. Remember that here one of the example that I have not mentioned, if at all if we don't find any whole integer of y, then we need to return -1 in the end. If at all if we can't find such number such that y power n is not yielding a result of m, in that case we will need to return -1 back to the user. Okay, so that is the problem statement that we have gotten. Now if you observe here, this is one of the problem that we can solve with the binary searching technique, right? If at all if you want to see the brute force approach, you can go to codingpal.org. there you can find the brute force solution anyway. But let's try to understand what is the better way to find the value of y here. So the better way of finding the value of y is nothing but using the binary searching technique. Now let's see how can we solve this problem with the help of a binary searching technique. Okay, so let's just assume the value that we have gotten for the n is nothing but, let's just say it is 2, and the value of m that we have gotten is, let's just assume 16. Now here to apply the binary searching technique, what we will do is we will need the range in which we need to apply the binary searching technique, right? That is the reason why here we need to have start and end. Start is nothing but 1 we will be doing, and end is nothing but whatever the value that we have gotten, which is 16. That is what we will be considering it as the end. So we will consider all the values in between 1 and the given value of m itself. That means here our possible range would be 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. So this is our start and this is our end. Immediately what we will do is we will try to calculate the middle, right? Because we are applying the binary searching technique. Middle is nothing but 1 plus 16 divided by 2, which is nothing but 8.5. So if we floor it, we will get 8. So this is where the middle that we have gotten. Immediately what we will do is whatever the middle that we have gotten, middle power whatever the n that we have gotten, right, we will perform that. That means that 8 power 2, 8 square is nothing but 64, but the value we want is 16 itself. That means middle power whatever the n that we have gotten is greater than whatever the value we need to find. That means that it is there on the smaller values. So the smaller values are there on the left. So immediately what I will do is end I will be updating with middle -1. So end will be pointing to 7 and start is still at 1. Now again I will calculate the middle. That is nothing but 1 plus 7 by 2, 8 by 2, which is nothing but 4. So middle is at 4 now. Immediately what we will do, 4 power 2, that is nothing but 4 square, which is nothing but 16, which is equal to the value of m. So immediately when we did middle power n, we have gotten the result. So we will immediately return middle as the result. Okay, so that is the simplest example where we had a whole number, if we performed that power n, we had gotten the valid value of y. Now let's just assume that just like this, here we have gotten n is equal to 3 and the value of m is equal to 16 that we have gotten. Now let's just try to see if we can find a whole number or not. If we can't find any whole number, we will be returning -1 in the end. So what we will do, we will start from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. So start we will be having it 1, end we will be having it 16. Here what we will do, we will calculate the middle. Just like previous case, the middle that we will get will be 8. So here is where the middle will be. So if we perform, what we will do, once we get the middle, we will perform 8 power whatever the value of n that we have gotten. So 8 power 3, which is way beyond whatever the value that we want. So immediately we will update the start to end to middle -1. So this will become our search range. So here again we will calculate the middle. Middle is nothing but, here what is the value of middle? So 7 plus 1 divided by 2, which is nothing but 4. So here is where the middle is. Again we will perform 4 power n, which is nothing but 4 cube, which is nothing but 4 into 4 into 16 into 4, which is nothing but 64, which is greater than 16 that we want. So immediately what we will do, we will update the end with, because we wanted the smaller number. Smaller numbers are there on the left. So we will update end to middle -1. So start is at 1, end is at 3. Again we will calculate the middle, which is nothing but 1 plus 3 divided by 2, which is nothing but 4 by 2, which is nothing but 2. So this is where the middle is right now. Now if we perform middle power n, which is nothing but 2 power 3, the result that we get will be 8. But the value we want is, what is the value we want? We want 16. 16 is greater than 8, right? That means the value will be there on the right. So immediately what I will do, I will update the start to 2 and end is at 3. So again I will calculate the middle. Middle is nothing but 2 plus 3 divided by 2, which is nothing but 5 by 2, which is nothing but 2.5. Again I am at the same position. So what I will do, I will perform the 2 cube, which is again 8. So I want the greater number. So again I will update the start with middle plus 1. So here I will be coming. So end and start both are at the same point. Whatever the number, even though they are equal, even that number can yield the result, right? There is a chance that. So immediately I will again calculate the middle. So which is nothing but 3 plus 3 by 2, which is nothing but 3. If I perform 3 power 3, what is the result? 3 into 3 into 3, right? 3 into 3 is 9, 9 3s are 27. Still the number is greater. So what we need to do, we need to move on to the left. So immediately end I will be updating with middle -1. So end will be coming to 2 and start is at 3. So we are overlapping the values. So here is where we can stop the binary searching technique. So ultimately, after checking all the possible values, what happened? We couldn't find any proper whole integer to which if we perform this power n, we could not find the yielding result of m. So that is the reason why here in this case, since we couldn't find whole integer, we will be returning -1. Okay, so this is the binary searching technique for finding the nth root of the given numbers according to the problem statement using binary searching technique. Remember, once we find the middle, we will perform middle power given n. If at all, if we are getting the given value of m, that is the result, so we can return that. Otherwise, based on the nature of the value, either we will search on the right part of the right part of the search range, or left part of the search range. Here the search range is nothing but where either from middle plus 1 index to end, or start to middle -1 index. Okay, so that is the binary searching technique for finding the nth root of a given number. Now that we understood the algorithm, let's quickly go ahead and write the pseudocode. and try to understand the time and space complexities, and later move on to the implementation of the same thing. So here what we will do, we will write find nth root of a number. What it does, it will take the value of n and it will take the value of m. Immediately for applying a binary searching technique, what we will do, start we will be initializing with 1, end we will be initializing with given value of m itself, and I will also define one variable middle and I will be initializing it with -1. Immediately for applying binary searching technique, as long as start is less than or equal to end, what I will do, I will calculate the middle. So here middle is nothing but start plus end divided by 2. Immediately what I will do, I will use some other math library or anything where I have already implemented the power function. So immediately I will call the power function, I will pass the value of the middle and middle power n I want to perform, right? So I will pass that. So here if at all this result is equal to the given value of m, then we found our number. So immediately we will return middle itself. If this is not the case, there are two scenarios, right? We need to search either on the left or on the right based on the result nature. So if the result that we have gotten is greater than the value of m, that means that we need to find the smaller middle. Smaller middles will be coming on the left of the whatever the middle that we have, right? So that is the reason why end we will update with middle -1. If this is not the case, then we want the greater values are there on the right, so we will update the start to middle +1. Okay, so this logic will suffice if at all if we have a proper result and we can return the value. If this is not the case, after executing all this while loop, after searching all of them, if we couldn't find anything, we will return -1 in the end. Okay, so this is the implementation for the basically pseudocode for finding the nth root of a given number. So ultimately here, if we want to analyze the time complexity, here the time complexity is nothing but for this while loop we will be taking log n units of time. Similarly here for finding the power function, we will be taking the log n units of time. So the time complexity is nothing but log n into log n. Now let's try to understand the space complexity. So the space complexity for this outer side while loop will be constant only, and here whatever the power function that we have implemented, it will also consume constant amount of memory only. As a result, the total space complexity for the logic of finding the nth root of the given number will be constant only, which is nothing but can get represented as order of 1. Okay, so that is the time and space complexity of the logic that we are going to write. Now that we understood the pseudocode and the entire algorithm behind it, let's quickly jump in and try to write the implementation of it and validate various scenarios.